morning, everyone. Welcome to the Reclaim Network Plus webinar series. So this is webinar 3 today. My name is Prashant Kumar. So I'm from the University of Surrey and one of the investigators on the Reclaim, the Network Plus. So just to introduce basically very briefly the team. So we got other colleagues. So today we have Dr. Thomas Kjeldsen on the call, so from the University of Bath. And there are colleagues from the University of Bangor, UKCH, and University of Warwick, who are the other co-investigators. We have our network manager, network fellow, and there are almost around 300 members who have joined so far the network, and that's growing over time. So just to say that Dr. Thomas Kjeldsen will be chairing the Q&A session today during this session. But before I go further, just a few housekeeping notes. So this webinar is being recorded, and that will be made available to our YouTube channel later on. So you can view this webinar in case if you wanted to share with other colleagues. But you can also watch the previous webinars from the same place, which are available, there. We will take all the questions and answers towards the end of the session. So we got 2 speakers today. So you can use the Q&A chat box, so you can see on your screen to write your questions, and you can add your name and affiliation if you wish to be read with your question. And Thomas is going to pick up your questions and read out to our the speakers towards the end of the this webinar there. If you're using the social media channels, you could you can use the Reclaim Network. So we are on the Twitter, and we are also on the LinkedIn. So just to say very quickly that this is a 18 webinar series which started a couple of months back, and this is going to go until the end of network time, which is March 2024. So we are basically trying to mix up the speakers so that we have the academics, but more importantly also covering the non-academic colleagues actually be coming from the different the groups, like either they are practitioners or policymakers or environmental groups, or from the governmental organizations. So the last webinar you see was on 6th of July, and the recording of this webinar, as I said, is available on the the YouTube channel there. Just to say very quickly that we have an open call for the webinar. So in case if you are interested to be any speaker, so either just send an email on to info@reclaimnetwork.org, or can send it directly to any of the co-investigators or the network team, and we will try to find a slot for you. The another exciting opportunity is the short knowledge exchange widgets, or the secondment call, which we released a month ago, and we just extended the deadline to 2nd of September. And that's an excellent opportunity to get a little bit of funding support for yourself to work with any of the collaborators you wanted to work to foster the knowledge exchange among your network in the area of the green, blue, and the grey infrastructure, looking into the urban sustainability. So you can see the call is there, and you can see the link in the chat box, which you can circulate among your network, or you are most welcome to apply to that. So today we got 2 speakers. So the first one is Professor Rakesh Mishra, and then we got Dr. Richard Baldauf. So they will be speaking one by one. So just to introduce Professor Rakesh Mishra, he leads energy emission and the environment research group within the school of just lost my screen, computing and engineering at the University of Huddersfield. And Professor Mishra is a co-director of the Center of Thermofluids, Energy Systems, and High Performance Computing at the university. Professor Mishra is an active consultant to many thermofluids industries and has run several knowledge transfer partnerships successfully. He's currently involved with several projects, including EPSRC, STFC, and Innovate UK projects. He's very active in renewable energy research and is involved with many renewable energy organizations. The developments of digital twins of various physical systems is currently one of the major research areas that he's focusing on. And just to add that, he's also one of the founding members of the Reclaim Network. He's going to talk about of this very interesting topic today. So without any further ado, I'm going to pass on this to Professor Mishra to take the floor.
Thank you very much, Professor Kumar. Thanks for your kind introduction. I will try to share my screen. Sorry about this. Thank you very much for inviting me, Prashant. And I'm going to speak about Lattice Boltzmann Model-based digital twin for an indoor environment. As Prashant mentioned, I'm Rakesh, and I'm Professor of Fluid Dynamics at the University of Huddersfield. I would like to acknowledge the help that I have received from Dr. Frankie Jackson, who is research fellow in the group. He's been the main brain behind Lattice Boltzmann model development, and some of the videos that you will see were created by him. So just an overview of the presentation. I will speak about what digital twins are and why they are more important nowadays, considered to be more important. Then what sort of technologies are there and how simulation methodologies are being integrated with digital twins for detailed information. And there can be a number of simulation methodologies, but we are focusing on Lattice Boltzmann method for specific reasons. I'll go through those reasons. I'll then show you the one of the houses that we have developed in our lab, that is Smart House, and the sensor setup that we have developed to create digital twin. And then how this Lattice Boltzmann method has been utilized for different types of boundary conditions, steady state transient simulations, temperature distribution, and then I will conclude with the main outcomes of the work. I must emphasize that the work is still currently ongoing. Like all over the world, there is lots of emphasis on digital twins. Our focus is on developing the multi-layer approach to digital twins and make twinning as high as possible. So let us go to the next one. What digital twins are? This is just a physical representation. I don't want to go much into technical, but what you're seeing on your screen left is the smart house that we have within the lab space of Huddersfield University. And on the right that you are seeing is a computer model which shows velocity vectors going from the door inwards. So basically, in a way, the picture on the right is digital twin of the picture on the left, or the physical object on the left. But there are many technical aspects with regard to this in terms of twinning, what is the level of twinning and all that, and I'll come to that a bit later. But for the moment, just for a basic description, we have a computer model and we have a physical model here. Now, slightly more detail about how digital twins act. So, for example, I showed you physical model here and digital model here. In this paper by Sajjad et al., they have very clearly outlined a physical asset and a digital twin of that asset. Basically, twins are twins to each other, but they are interacting with each other in real time. And for that interaction, we need to have an IoT platform. So we need to have a number of sensors put in physical asset, and these sensors in real time must interact with the digital twin that we have on our computer screen. And both will have capability of affecting each other or affecting each other's operation. So let us come to slightly more technical, what digital twin is and how do we define it. There are lots of definitions, and because there are a plethora of activities currently in this particular area, digital twins mean different things to different people. If you go through literature, lots of definitions. I like this definition that this is an integrated multi-physics, multi-scale, possibly probabilistic simulation of a complex product that uses best available models, sensors, and updates all the processes in the computer model, which indicate what is happening into the real twin. So lots of things are needed, like in this, which includes many technologies, Internet of Things. We need big data, machine learning, cloud system, and virtual reality. I'll go step by step into this with a bit more detail on how these things are used and how these things can be integrated, and then how these things can be used for green, gray, and blue infrastructure, and how this adds to sustainability and all those aspects I will cover a bit later. So in a nutshell, a digital twin has three components. So we have a physical system, as I showed earlier. We have a cyber system that works on computer, and then we have a cyber physical system that works, that combines the physical system with the cyber system. So cyber physical system is sort of a brain that acts between the physical system and the cyber system, and where lots of technologies come in. So the key technologies that we need to have in the digital twin is, first, like we have been hearing IoT for a long time. So we can connect a number of physical devices via the internet without human to machine interaction, almost in real time. So this is the first technology that is used in the creation of digital twin. So we can put sensors, wireless sensors, and they will give us data in the real time for us to make inference from that. The second most important thing is cloud computing, because most of the data that is generated from the sensors can be stored in cloud, and then it can be used by user, or it can be manipulated by user for getting their simulation models to get more information about their physical asset, and also to maintain connectivity between the physical model and the twin model. Cyber physical system, as I mentioned, this is the most important aspect of a digital twin, because it maintains the connectivity between the physical system and the computer system or the cyber system. So it involves lots of control system which can affect, like using a digital model, we can affect operations in the physical system. And any change that is happening in the physical system is monitored by sensors, and that gives information to the cyber system. So there are lots of examples of this: SCADA, robotics, autonomous vehicles, smart grids, and autopilot avionics. These are some examples of where this type of technology is already being used. So what has happened is, so all the technologies are available, and now if you go through literature or the funding opportunities or types of projects being awarded, you will notice that digital twins are being developed in almost all the areas, including health sector, infrastructure systems, natural systems, physical systems, and all that. So as I mentioned, digital twins mean different things to different people. So here I would like to classify some distinction between what a digital twin is and what we wish to achieve. So in classical engineering sciences, what we have is, we have a physical system, and then we have our simulation. So using any computer model, we create that physical system on the computer, and we try to assess how this physical system is performing. But this is done offline. For example, if we want to model indoor environment, we create model of indoor environment, we put some boundary conditions that we expect physical system to act with, and then we try to see how physical system is going to behave. So that is typically offline simulation. The next stage, more intensive stage for that, is online simulation, where we have physical system, we have sensors in the physical system. These sensors are giving us data in real time, and that data in real time is used as boundary condition for simulation, which are equally fast and give us information about how our physical system is behaving almost in the real time at very, very local level as well. We don't need simulation if we need very discrete information. But for example, if you have a high performance computing center and you just have one temperature sensor there, temperature can vary very widely within that high performance computing center, and you would like total temperature field there. So in that case, you may need either to have hundreds of sensors or a few sensors and a simulation methodology to find temperature distribution. So that is online simulation. The digital twin allows us online simulation and control. So in this case, what happens is we have physical system, we have sensors. These sensors are providing us data for digital system where we can carry out very fast simulations. But at the same time, we have capability of controlling how physical system behaves from our digital system. So this is our aim of creating a digital twin. Okay, so ultimately why it is needed, I can list many pages on this, but just from our point of view, some useful information. So local versus global flow field. So from measurements, putting some sensors here and there, you can find some information on how different things are happening, how different processes are taking place. But digital twin allows us to monitor entire space simultaneously. So it gives us local information almost simultaneously. The second thing is tracking of pollutants. For example, if there is a pollutant in an indoor environment or in any environment, we can see how pollutant will evolve and then how we can carry out, how we can develop mitigating strategies for that, and almost in real time. So evolution of any process, we can track with digital twin, and we can take any corrective measures. We can control the environment through proper actuation mechanisms or through systems developed for controlling the environment. We can design control system. We can improve energy efficiency of our heating and cooling system because we'll know locally how the comfort conditions will be across the space. So what will be energy needed for that? We can monitor performance of systems. So performance of indoor environment, performance of entire physical system, we can carry out using digital twin. The most important aspect is we can real-time monitor how things are at different points in the place. And taking slightly more advanced, we can put assistive devices within those indoor environment, and those assistive devices can be used to help the people living in that particular environment. So we are working something in that area. As I mentioned, there are many other applications. That's why many researchers, many colleagues are working in different areas trying to develop digital twin. This is my initial attempt at developing a digital twin for indoor environment. Now, as I mentioned earlier, that we need a physical system, we need sensors, but we also need simulation methodologies. Now, one of the simulation methodologies that I have chosen is known as Lattice Boltzmann method for an indoor environment. And there is a reason behind it, although there are many number of simulation methodologies and one can choose any. But I've chosen Lattice Boltzmann for this particular case. Also, we have expertise in other methods which are more useful at microscopic scale as well. Just to give you an indication, I don't want to go into much more technical depth of the method, but just to give you an overview of how this method works and then how we can use it for digital twin. So you can see this picture on microscopic scale. If we take about 1 centimeter by 1 centimeter by 1 centimeter volume, in that volume, there'll be approximately 10 to the power 23 particles, atoms, molecules. Now, using Newton's second law of motion, force is equal to mass times acceleration. If I want to find how different particles are moving, then I have to solve 10 to the power 23 equations. And we need very fast computers with huge memory and then we can see how different things are evolving, different processes are evolving. So that is at the molecular scale, and which our computers cannot handle at this moment in time. Then comes the macroscopic scale, where we typically use Navier-Stokes equation for flow modeling. So in this case, what we do is we take an average behavior of the fluid particles and we take a continuum approach in solving the equations. One of the disadvantages in macroscopic scale is, okay, fine, A is time. It takes time to do that. But second thing, there are lots of approximations in the, for example, if flow is turbulent, which turbulence model to use, and if you go for higher order turbulence model, the time increment goes further. Now, LBM works between the microscopic scale and macroscopic scale. So this is known as mesoscopic scale. So that's why we preferred, because in an indoor environment, suppose if we consider an indoor environment, the number of processes that are taking place are at different scales. For example, if we talk about decontamination or cleaning, this is taking place at molecular level. Whereas pollution dispersion or things like that, velocity change and things like that are taking place at a highly macroscopic level. So we would like to have a method that can cover range of operations or range of processes taking place. So that's why we took LBM as a method, although we have also worked with macroscopic method for the same purpose. It is possible to have very efficient computational schemes. So we can have parallel computing algorithms for LBM, and we can almost get real-time performance from this as well. This is especially suited for porous media flow. So for green infrastructure design, this can be very, very useful because we can track pollutant motion across porous media. So if you think of a hedge, how pollutants are moving across the hedge, how many are trapped, that can be done quite efficiently, and probably suited for blue-black gray infrastructure monitoring as well. So this method has lots of potential. It's in the process of development, but I think in years to come, this method can be used very successfully.
Apologies, Rakesh. Can we sum it up in less than 5 minutes?
Yeah, that's what my plan is. Okay, so this is the example of my the smart house. You can see this how it looks: washroom, the living room, and this the kitchen. And you can see we have placed sensors everywhere in the smart house, and we have pressure, temperature, humidity, motion, distance, carbon dioxide, PM 2.5 sensors. We also have thermal cameras, so we can monitor lots of activities within the smart house. And this is the type of real-time signature that we get from the smart house. So you can see when there is a motion, this motion detector observes some motion from someone coming in, and this shows that signature on temperature and humidity. So also increase in CO2 concentration. So we can in real time monitor if things are happening and how the occupant behavior is affecting the indoor environment change. We could also see that this PM 2.5, although we are mentioning that it did not correlate very well with the arrival and departure of people in that. So this is some of the information that we got. We can average out and we can get overall information about the smart house pressure, temperature, and even we can monitor the central heating system performance, because that is also being properly instrumented. This is an example of sensor map. So on the left, you have ground floor, and on the right, you have the top floor, and you can see number of sensors we have put in there, different types of sensors. Okay, so this is the sensor part, and then we have integrated this with the simulation methodology. So this simulation methodology is, as I mentioned, based on LBM method. This is basically, it started with cellular automata, which says that the state of a particular cell in future will be dictated by its neighboring cells. And there can be 256 rules for one-dimensional cellular automata. And I'll just show you a video here just to demonstrate to you how using cellular automata we can predict the future states of the cell. So this was the basic okay. So this is the smart house. We have shown you the sensor, we have shown you the building, and then we have carried out simulation from the data that we have got from the sensors. And as you can see here, this is the local velocity field inside the smart house, both for laminar flow and turbulent flow that we have been managed to get through Lattice Boltzmann model. This is just to demonstrate to you how the effect of people coming through the front door is having on the velocity field inside the smart house. This is the effect of heating through radiators. So I have just created one plane. I can create as many planes as we need to have a real-time visualization of what is happening in the smart house. And this is the real-time data from a radiator that is being used. So you can see the color of radiator changing. And you can also see in the real time how the thermal plume is being generated and how buoyancy-driven convection can be monitored almost in the real time from the data obtained. So this is just to demonstrate that we have been able to model and integrate sensors with the real-time simulation. It is still in the process of development for the refining, but we have at the basic level, we have managed it. And through this, we can almost in real time monitor any processes taking place in the smart house. We wish to take it further, and I would welcome any collaboration opportunity. And if you want to visit a smart house, please feel free to contact me at r.mishra@hud.ac.uk. Many thanks for listening, and I'll be very happy to answer any questions at the end.
Thank you, Rakesh. I think we'll take the questions in the end. So if you're listening to this presentation, please leave your questions using the Q&A chat box. Thomas is going to chair the session and he'll pick up those questions. So I have a pleasure now to invite our second speaker, Dr. Richard Baldauf. Dr. Baldauf has over 20 years of experience conducting research on emissions, air quality impacts, and adverse health effects from exposure to air pollution emitted by transportation sources. His research focuses on the development of policies and practices to mitigate air pollution emissions and impact at local, urban, and global scales. He works for the United States Environmental Protection Agency's Office of Research and Development, where he leads cross-disciplinary research teams focusing on air quality measurements, air dispersion modeling, and sustainable urban development. He also maintains adjunct professorship appointments at North Carolina State University and the Texas A&M University in the US. He will present on his research today investigating how urban green infrastructure affects air pollution, especially in communities located near large roadways and other ground level air pollution sources. So thank you very much, Richard, and we are looking forward to hear your exciting work around the green infrastructure today.
Yeah, thank you so much for the introduction and the invitation to speak here. And yeah, this will describe some of the work we're doing in the United States, although we're doing this a lot in collaboration with others worldwide. So this will just kind of be a very brief overview, though, of some of our activities and research. And so we can go to the next slide, please. And as many are aware, there are quite a few tree planting programs occurring worldwide. We have programs such as the global one by the United Nations, the Trillion Trees Initiative, but there's also many projects being implemented throughout the world, many looking at like climate adaptation and mitigation, stormwater management, which is a very traditional approach when people consider green infrastructure, but also for urban cooling, CO2 sequestration, and other, especially climate-related concerns most recently. So really what I'm going to talk about, though, is more recent research that's showing how green infrastructure can be used for air pollution mitigation. And in addition to like CO2 sequestration, Also mitigation for select short-lived climate pollutants, especially black carbon. And so I'll get into a little bit of information about some of that work. And I did want to highlight, a lot of this has come again from both programs in the United States as well as international programs. One especially that many of the Reclaim Network participants were part of, with the iScape program from Horizon 2020, but we do also have some active and planned projects here in the United States. We've actually just recently signed a bilateral agreement with the Polish Ministry of Climate to implement some projects there, as well as some work we're doing in Peru. So just want to highlight that's where a lot of this information has come from, these different collaborations. So we can go to the next slide. So for an overview, I'm just going to give a very quick background, air pollution concerns, SLCP concerns, and again, how we can use green infrastructure as a way to mitigate those concerns. What are the mechanisms? What's some of the research, as well as some of the recommendations that we've developed based off of this research. And of course, I always like to highlight when we're talking about especially urban green infrastructure or the many co-benefits that occur as well, not just the air pollution benefit. So we can go to the next slide. So again, I won't get into too much detail on the background, but many are aware this is an image from the United Nations Climate Clean Air Coalition program, but we see a lot of this evidence from the World Health Organization and many agencies throughout the world. Just air pollution is one of the largest contributors to death and illness worldwide, especially concerned about exposures to particulate matter. And this can occur from respiratory and cardiovascular effects, but effects across the board, even birth, developmental. And we can go to the next slide. That in addition to air pollution in general, exposure to traffic emissions has been linked with an even increased risk in adverse health outcomes from just air pollution exposure in general. So we're really concerned about people who live, work, go to school near large highways, but also other transportation facilities like rail yards, ports, anything, where people are really exposed to fresh emissions, direct emissions. And again, we see these health endpoints from respiratory to cardiovascular, but again, we have birth, developmental effects, cognitive effects. We're especially concerned with children. And this graphic is from a recent meta-analysis done by the Health Effects Institute in the United States. But it's also important to note they didn't look at all health endpoints. There's been other meta-analysis looking at like childhood leukemia, cognitive development, neurological effects, even including autism. So again, a lot of health concerns associated with exposures to traffic emissions, especially particulate matter. So we can go to the next slide. And again, one of the reasons we've been especially interested in transport sources is air pollution can just be highly elevated. Especially, very close to roads. Even with high background concentrations in urban areas, we can still see elevated concentrations within the first 200 to 300 meters of large roadways, sometimes an order of magnitude higher for certain pollutants that are especially associated with fresh vehicle emissions. So we can go to the next slide. And then I did also want to mention how we can get these climate benefits. Again, green infrastructure, very commonly known about CO2 sequestration. But again, we have this concern over the short-lived climate pollutants as well, especially black carbon and methane. So I'll talk a little bit about that as well. But for us to reach our global climate goals, mitigating these two pollutants will be extremely important, especially in the short term. So we can go to the next slide. So again, when we look at mitigating transport emissions, very historically, we're talking about, reducing just vehicle direct emissions. That's the traditional mission, really, of many environmental agencies, including my own here in the United States. But we also look at other methods. We want to reduce vehicle use and activity. But then we started a lot of this research because we wanted to also investigate, how can we look at urban design, transportation planning, that can actually also reduce people's exposures, again, especially to these ubiquitous sources like transportation. So we can go to the next slide. So this graphic just gives a brief overview of how green infrastructure can improve, especially local air quality and reduce emissions. And there's essentially two mechanisms. One is that the vegetation, if again designed properly, it can increase just dilution and dispersion. So a little more mixing, the pollutants have to travel further before they reach the person being exposed. So there's a reduction in concentration. But vegetation can also have a filtering effect, especially for either smaller or coarser particulate matter, as well as some gases can also be absorbed onto the leaf surfaces. So again, there's this dual mechanism. So we actually can get, again, under correct designs, we can get some actual reductions in the overall emissions, not just an increase in dilution or dispersion. So we can go to the next slide, please. So for the sake of time, I won't get into a lot of detail on the research, but I did want to mention, I'll focus a little more on the recommendations and summary of this research, but I did want to let the listeners know this is grounded in research, not just in the United States, but worldwide, and including a lot of work done in Europe. But this is just an example where we can see particulate matter, again, especially the real small ultrafine particles. So when we look at particle number or black carbon, we can see very significant reductions, even as much as 50%. We can go to the next slide. But again, as I've been mentioning, the characteristics of the vegetation is extremely important. So this is a study where we were looking at different types of vegetation, some very thick, tall, full coverage, but others with gaps, either dead trees or spaces within the trees. And we see very, very mixed results. And so we could see, again, with very full coverage of vegetation, again, we could get reductions in PM number for ultrafine particles over 50%, reductions in black carbon around 25%. But as you see here at the location 3, when we have very high spacing, we have lots of gaps, we can actually either get no reduction from the vegetation, no improvement, and even actually sometimes a worsening of downwind air pollution. What happens is the vegetation can cause some stagnation and a buildup in pollution downwind. So again, the design characteristics are very, very important. So we can go to the next slide. And again, as mentioned, this is grounded in research. I pulled 4 review articles that have been done. Again, a couple of these by participants in the Reclaim network as well. And so I think these are very useful resources for folks that are interested in this topic area. They each deal with slightly different aspects of this, but can be a very useful resource, and wanted to make sure these were available to listeners. And so we can go to the next slide. And also, in addition to publishing in the scientific journals at EPA, we've put together a recommendations document, really again to highlight what are these characteristics that are important. And so this recommendations were actually used for some design projects, and we developed them for implementing projects, both in the US, and it was actually used in a couple of European projects as well. And so really, again, what we were trying to focus on is giving the information needed so designers could really maximize potential pollutant reductions, and then also avoid those unintended consequences like I showed in that previous slide. So we can go to the next slide. And this is just a real quick summary and just some examples of, in this case, some potentially effective roadside vegetation barriers. And so, as I mentioned, we really need thick, as tall as possible, but usually we're talking at least about 3 to 4 meters in height. But again, coverage from the ground to the top of the canopy, no gaps, no dead trees, and maintenance is very, very important in this case. Hedges, again, we know hedges very popular in the UK and other parts of Europe, Not quite as popular in the US, but it's actually growing. And this bottom example is actually from California. But again, we've seen a lot of research showing how hedges, again, if they're thick and very healthy, they can be an effective roadside barrier. So we can go to the next slide. And again, in addition to what's effective, we really want to highlight, types of vegetation and design characteristics to avoid in our guide. So these are just a few of the examples from the guide as well. We especially like to highlight the top left picture because often when we talk about planting roadside trees, people think of this type of ornamental tree, nice big canopy, very aesthetically and visually pleasing. However, again, not effective and can actually worsen downwind air pollution because the pollution plume from the vehicles can actually go underneath the canopy. The air will follow that path of least resistance. So we can get a concentrating effect underneath, but also the canopy can slow winds again and cause a stagnation effect and again, increase pollutant concentrations under and downwind of this kind of vegetation stand. And then like the bottom middle, again, is just importance of if people are planting and developing, a vegetation barrier, how important maintenance is, because if you have gaps, like is shown in, the bottom middle picture, either dead trees or just, this is where we ought to talk about seasonal effects as well, where we want plants that maintain their integrity year round for effective barriers. Because if we have these kind of gaps, again, pollutant can funnel through, but wind speeds are reduced and we can see increased concentrations. And this is actually from one of the research studies that I had mentioned. And then in urban canyons as well, the bottom right. Again, a lot of research has shown that if we have just canopy-like trees spaced too far apart, we can again get stagnation in the canopy and an increase in pollutant concentrations. We can go to the next slide. And the last thing I did want to mention, the recommendations, is research has really shown if we can combine solid like fences, solid noise walls, other solid structures with vegetation, we can really actually maximize pollutant reductions because the solid structure ensures that we get that dilution effect off the roadway away from especially for people at breathing level height. But then we get the added benefit of the filtration from the vegetation. And so a lot of research has shown that this really maximizes downwind pollutant concentration removal. So we can go to the next slide. Again, I just wanted to show a couple conceptual approaches and applications. Again, we have these situations like shown in the top left, especially large roadways with open areas. And again, exposures, as I showed earlier, can be very high. So for some pollutants, an order of magnitude higher and a short distance from the road. And so this gives us a lot of opportunities, though, for planting as well and to increase green infrastructure for air quality and, again, the other benefits. And so there's just an example of several types of planting applications that could be done in that kind of situation. And then, as I just mentioned in the bottom, a lot of cases we do have these, walls and structures for sound mitigation. But then we can also use those as planting opportunities as well and get an even further increase in air pollution reduction. So we can go to the next slide. Again, when we're talking about urban canyons, and they're very much more common in Europe, but also very common in many of our megacities throughout the world. More complex situation, a little more difficult to deal with, but again, research has shown that like low walls, some low hedges, or even combinations of the two can improve air quality at the street level. But then we can also talk about other benefits in greening in these kind of situations by also adding green walls, green roofs, and other types of green infrastructure to, again, especially increase some of the other benefits as well. So we can go to the next slide. And again, just included in our recommendations, there are many other considerations. Vegetation characteristics, species is important. Obviously, native versus non-native, how robust and healthy are they going to be from planting, especially the near road environment, can be very rough. You can have treatment, other chemicals from vehicles, so they have to be very robust trees. But then also for the region, is it a dry region? Is it prone to flooding? Other kinds of situations like that are very important. And then, as I mentioned, the physical characteristics. In addition to what I've already talked about, other things like the leaf surface themselves, either waxy or sometimes like a hairy leaf surface, can improve, especially the retention of PM removal, where it stays on that leaf surface and doesn't get re-entrained during high wind events or other kinds of situations like that. And then also very important, we don't want vegetation that can actually emit pollution like VOCs, pollen, or other allergens as well. And so we get into that in our recommendations as well. Can you go to the next slide? I'll be finishing up here in a couple minutes. I did just want to point out when it comes to selecting species, there's a number of programs worldwide. Many countries actually have like programs or tools that can help with species selection. This is just highlighting one we have from the US, our US Forest Service. It's called iTree. Although this model, I do point it out because this model is global, so it does provide information on tree species throughout the world. And so several of the countries that don't have their own databases do often use this model as well. And so this can help again with species again that don't have seasonal effects, that are more native or robust for a certain region, but then also don't emit high levels of pollutants and other sources of concern. We can go to the next slide. And then lastly, again, we always like to highlight the co-benefits of planting urban green infrastructure. Now, there's many opportunities, and air pollution reduction is just one. As I already mentioned, there's CO2 sequestration, but then I talked about earlier the importance of the SLCPs. Again, a lot of evidence of methane removal from vegetation soils. So if we're increasing some of that planting near roadsides, that gives us also a potential sink for methane. Again, improved urban cooling, reduction in stormwater, water quality, some noise benefits from vegetation. And again, lastly, just to highlight, many health studies have just shown exposure to greenness or just, people being around vegetation and other types of green spaces can just overall improve public health. So again, a very important consideration. So we can go to the next slide. And again, I'll just highlight real quickly, this is just showing some of the co-benefits. So again, I think many people are aware of the potential urban cooling effects by increasing and maximizing our green infrastructure in urban areas. We can go to the next slide. And lastly, as I had mentioned, traditionally stormwater management has often been even the term for green infrastructure, at least here in the United States. So again, we really want to highlight how in many cases, we can also integrate an air pollution benefit as well to a planned stormwater project and kind of get, again, the multiple benefits and don't lose any opportunities for air pollution improvement. So with that, we can go to the next slide, just my concluding remarks, but for time, I'll just, transition now to the question and answer if we're ready for that.
Thank you very much, Richard. This was a fascinating presentation. I'm going to pass on to Thomas actually to chair this Q&A session.
Thank you. Thank you, Prashant, and thank you to both speakers. I guess we can, if you have any questions for the speakers, you can type them in. We don't have all that much time. But we had a question from on the Q&A from Emma Ferranti asking Rakesh, so what are the links between the research, the fundamental research you're doing on your digital twins, and what are the links to the blue and green infrastructure? Where do you see that link?
Thank you. Yeah, it's a very good question actually. So the work that we have done up until now is creating digital twins for basically various physical systems, mechanical systems, and now we have extended it to monitoring of indoor environment. So the main use of digital twins is monitoring performance of different systems. So I provided the framework. So you have a sensor which can sense various process parameters. And then you can have a machine learning or a simulation or any type of model that can basically use that data to predict and monitor different variables corresponding to green, blue, and other infrastructure for better performance. So the framework is there, and now it is for us to think about how do we apply to all those. Like currently, we are using it for mostly for pollution control or pollution monitoring, and developing mitigating strategies. And the same thing can be carried out for green and blue infrastructure.
Thank you. So we also got a question coming here for Richard from Karina, who asks, what are the actual percentages improvements that you're observing following your greening of your urban space?
Yeah, well, thanks. That's a great question. And that's like we try to highlight is that it's very, very dependent on the vegetation characteristics. So again, as I tried to show in that one slide, we could get reductions again, especially in ultrafine particles, as much as 50% or even a little more than 50%. We saw black carbon reductions around 25%, NO2 reductions around 20%, CO reductions around the same. But again, that's with a fairly thick and high vegetation barrier. Once we get away from those kind of ideal characteristics, so I would look at that as probably around the likely maximum that we can see in reductions. And then once we have a little more maybe porosity, a little more spacing, then some of those reduction amounts can go down. And again, though, if we have too much spacing or a situation like I had shown with canopy trees, then we can actually see increases downwind. So again, the characteristics are extremely important, and that is one of the next steps that we're working on is developing models so that we can make these estimates of what are the reductions based on different design characteristics. And I think through the Reclaim network, and I'll let Prashant jump in, there's a model being developed, especially for hedges, that allows some of these calculations as well, correct?
I think we have, thank you, Richard. I think we have more questions coming in, but I'm also mindful that the time set aside for this webinar is running out. So I'm afraid we won't have time to go through all of them. I have a lot myself. So I think we'll have to end the Q&A session here and hand back to Prashant.
And I'll just mention, if the slides are being shared, I have my contact information. I'm happy to answer any questions if folks want to send them my way.
Thank you.
Yeah, thanks.
Thank you, Richard, and thank you, Rakesh, and thank you, Thomas. I think it's been an exciting session. So we'll have all these the recording available to our YouTube channel later on as well. Before we close the session, I would like to announce the next webinar, which is on 7th of September. So you can see that we got two exciting speakers. So the first one is Richard Baldauf. So he is the managing director of the Biotecture. So I know Richard for a long time. They have been doing a fantastic work in installing green walls. And I can see there were a lot of interest actually from the members of the network. They wanted to know more how we can install them and what they can do and so on. So you may wanted to join this webinar. And another one is from Dr. Amy Owen. So Amy is the coordinator of this large EU project called Vegetative, which is basically looking into the nature-based solutions to reduce hydrometeorological risk in mountain areas. So they have been doing quite a lot of the case studies. So I think this will be another very interesting webinar to attend. So with that, I would like to thank all of you and our event team and colleagues who have been supporting, these webinars. If you wanted to know more about the network, so you can see there's a reclaim-network.org. So all the information is available there. You can also follow on Twitter, which is reclaim_network, and the LinkedIn group. So to know more about the activities and the upcoming funding and other collaboration opportunities from the network. So with that, again, I would like to thank all of you to join this webinar and our speakers for the fantastic presentations. Thank you very much all.